Now we are going to start with the hydrogen spectra as explained by the Bohr model. See, so we are going to start with the hydrogen spectra, right. So actually what Bohr said, he said that we know that hydrogen hydrogen is an atom, right, with one electron in it. We know that its atomic number is 1 and mass number is also 1. So proton is 1, neutron is 0 and electron is again 1. So if I try to write the electronic configuration, then its electronic configuration is also 1. So if I draw an atomic model, then that means proton is 1, neutron is 0, there is one shell having one electron. Right. So he said that what happens in the hydrogen spectra actually, in this what happened that when we supply this electron with an energy, greater than its own energy, suppose we say that here this electron has X energy and we supply it with Y energy and Y energy is greater than X, then only what will happen? This electron will absorb the energy and get excited to the higher energy state. Higher energy state means what took place? Excitation took place. What took place? Excitation. Then this electron remain here for certain span of time and then ultimately return to its original shell, and by doing so, what does it do? It just release the energy absorbed by it. Like we supplied it energy, it absorbs, get excited to the high energy state, remain there for certain period of time and then returns to its original shell, and when it does so, it just release the energy absorbed by it. And that energy release is equal to the energy difference between the two shells. For example, we say here the energy is E2, here the energy is E1. So when it will return to its shell, then it will just release the energy absorbed, which will be equal to the difference between the energy between the two shells. Now we can actually know about the frequency and wavelength also of the radiation which is being emitted. Like as we know that radiation is emitted when an electron jumps back, then that radiation will be having certain frequency and certain wavelength. So we can actually have a formula, or we can actually calculate the frequency and the wavelength emitted. How? As you know here, like if I put the value of delta E by Planck's quantum theory as h nu, this becomes E2 minus E1. If I need to know about the frequency, so this is my relation, that E2 minus E1 upon h. So this is how we are going to calculate the frequency of the radiation emitted when an electron jumps back to its original shell. Now we also know the relation between frequency and wavelength, which is nu is equal to c over lambda, and we can also write in terms of lambda that we can substitute this value here. So substituting this value here, we get c upon lambda is equal to E2 minus E1 upon h. We can just shuffle them up. So what do we get here? We get that lambda is equal to hc upon E2 minus E1. This goes here and this comes here. So by this relation we can actually come to know about the wavelength of the radiation which is being emitted. So this is what I think you got it, that how Bohr actually explains it. He explained that when an electron is its original shell, it neither lose or absorb energy by itself, but when we supply it with the energy greater than its own energy, it gets excited, and excited state being unstable, it returns to its original shell, and in doing so it emits radiations, and that radiation, the energy possessed by those radiation is equal to the difference, and we can also know about the frequency and wavelength of that radiation. So this is how the Bohr actually explained. Now one more thing must be striking your mind, that is that as we know that each hydrogen atom has only one electron, right, but when we talk about the spectrum of hydrogen, I told you that there are so many lines that appear, so many bright lines that appear, that we actually divide those lines into different series. That is, when into Lyman series, the lines which lie in a visible region, right, there are which lie in a Balmer series, that means the series of lines that lie in a visible region, and there are lines which lie in the infrared region, that is Paschen, Brackett and Pufund. So they lie in a infrared region, you know that. So you must be thinking that hydrogen is an atom with a single electron, and we are getting so many lines. So why the simultaneous appearance of lines occur? You know that what is the reason behind? The reason is that when we are studying the emission spectra, then because when we were studying the emission spectra, then only there were so many bright lines. So when we are studying the emission spectra, we are not taking one hydrogen atom. Keep in mind, we are not taking one hydrogen atom. Instead of that, we are taking a hydrogen sample. What we are taking? We are taking a hydrogen sample. And this sample will contain many hydrogen molecules. It will contain many hydrogen molecules. So when we supply it heat, because we know that to study an emission spectra, we there is a chance that a substance has its own light, or it emits light when we just heat it or pass an electric discharge. So in this case, to study an emission spectra, we need to pass heat or we need to pass an electric discharge, right? So what we do is, whether we supply it with electric discharge or whether we heat it, what is going to happen? Hydrogen molecule will break up to form many hydrogen atoms. Many hydrogen atoms. And we know that each hydrogen atom has one electron in valence shell. So as there are so many atoms, so that means so many atoms means they will be having their own electron. So when you supply it with energy, then electrons of all those atoms, I am talking about electrons of all those atoms, get excited to different energy levels. So when we supply energy, they get excited to, means I am talking about all the electrons which are present in atoms, different energy levels. They get excited to different energy levels, and we know that ultimately they need to come back to their original shell. So when they come, they may come in one jump or they come in multi jumps. When they come to their ground state, either they come in one jump or they come in multi jumps, and each jump just corresponds to a line in a spectra. Each jump corresponds to a line in a spectra. For example, I am just trying to explain you diagrammatically. Let's say that electron is here in first shell. Then when you, let us make the other shell also. 2, n is equal to 3, n is equal to 4, because we have different series. So what happens if we say that electron get excited, let's say it get excited to this level, and it need to come to n is equal to 1, then this might happen that it directly jumps into n is equal to 1, or there is a chance that it may come first in 2 jumps, that first into third shell, and from here it comes into first. So that means here it is making 2 jumps. There is a chance that it may come here in 1, then from here to here, and from then here to here. So it is coming in 3 jumps. So there is not a definite pattern that when an electron comes from an excited state to a ground state, it is coming in one single jump or it is coming in multi jumps. So any electron which comes in a different number of jump, and each jump corresponds to a line in a spectrum. That is why, as you are having so many atoms means you will be having so many electrons, and they will get excited to different energy levels. So when they will come, they will not come in a single jump. They might come in a single jump, they might come in 2 jumps, they might come in 3 jumps, or they might come in multi jumps, and each jump corresponds to a line in a spectrum. So that is the reason you get multi lines in the hydrogen spectra, that you need to divide them according to the region where they are occurring. Like Lyman, you know that n is equal to 1 is in Lyman series, n is equal to 2, 3, 4, 5 and so on. Then we discussed about the Balmer formula, that Balmer gave actually the formula in order to calculate the wavelength of the radiation emitted which lie in the visible region. Then it was transformed into a Rydberg formula. So Rydberg was a scientist who gave a formula in order to calculate the wavelength of any radiation of any region. Then what was that actually? It is wave number, which is equal to 1 upon lambda is equal to r. This is Rydberg constant, 1 upon n1 square minus 1 upon n2 square. This is the original ground state. This will correspond to a ground state, and this is going to be in an excited state. And Rydberg constant is 109677 per centimeter. So this you are going to use as Rydberg formula in order to calculate the wavelength of the radiation occurring in any of the region, whether it is Lyman, Balmer, Paschen, Brackett or Puffin. That means it is not limited to only Balmer. It is applicable to all kind of series. So I think you got it, that how to explain an hydrogen spectra on the basis of the Bohr model. So this is the emission spectra. So whenever you get a question like this, in order to explain hydrogen spectra, just first explain that what is the cause of spectra, that is the excitation process, how you can determine the wavelength and the frequency, then why the simultaneous appearance of lines are there, just explain it, then draw the figure like this also, where you will show that clearly that how the electron is returning, that it is returning in a single jump or in a multi-jump. And then after doing this, you need to mention the series also, that in which regions they lie. Like as you saw that Lyman is n is equal to 1. So that means the ground state is 1 and the excited state can be 2, 3, 4, 5, any of it. Like in Balmer, n is equal to 2, that means ground state is 2 and the excited state can be 3, 4, 5, 6, any of it. So that means excited state is always greater than the n, this n. And moreover, I told you about the Rydberg formula also in order to calculate the wavelength emitted by the radiations of the radiations in any of the regions. So this is all about the hydrogen spectra explained on the basis of Bohr model. So this is the hydrogen spectra explained on the basis of Bohr model, and it is one of the usefulness of the Bohr model also. Right. So this is what about the hydrogen spectra.